Right, let's get 13 marks in under 13 minutes. If you manage to do this question without any of the different parts I, and III, then well done to you. In the first part, we're just asked to find the complementary function for 2 marks. When we're looking for the complementary function, we turn the original function into some kind of quadratic equation. I like to use lambda, you might be used to using m or a different letter. So I'm going to change the second derivative into lambda squared, and I'm going to just forget about this cos x on the right. There's no first derivative, so I'm going to put 0 at lambda. You could just leave it out if you wanted to. And then the y, I'm just going to put plus 1. There's only one of them. As I say, make it equal to 0 because we forget that the cos x exists. Now I'm going to solve this. Lambda squared is going to be equal to minus 1. Therefore, lambda is going to be equal to plus or minus I. No time to forget your plus or minus in further maths. If lambda is equal to plus or minus I, that means the complementary function is of the form e to the, well, there's nothing there, there's no real number there, so 0x. Cos of is going to be 1i, so it's going to be 1x, and sine of 1x. And then we also want some constants, so I'm going to add a little a before the cos x and a little b before the sine x. So all in all, after we simplify, e to the 0x is just 1, and our complementary function would be a cos x plus b sine x for 2 marks. In the second part of this question, we are told that this funky expression is a particular integral of the said differential equation on the left-hand side there. And we're asked to show that p minus 2 lots of p plus q sine squared x is equivalent to 1. So I'm going to take their word for it that it's a particular integral, even though it doesn't seem very nice. If that's the particular integral, then I'm going to need to take this, differentiate it twice, and once I add it to y, I should get cosec x. So if I need to differentiate it twice, surely I need to differentiate it once. So really, this is the step that you could get lost in. So I'm going to write down the first part of the product rule, and then I'm going to write down the derivative of the second part. Then I'm going to write down the second part, which is, you might call it v, and then I'm going to differentiate the first part. The first part is differentiated by, well, p is a constant, that's just going to remain. To differentiate ln sine x is going to be 1 over sine of x times by the derivative of that sine x, which is cos x. So it's a multi-step product rule combined with the chain rule. We've not even done that, we're only halfway there. The next one is a bit easier though. We're going to write down qx, differentiate cos x, and then I'm going to write down cos x, and I'm going to differentiate qx, which is just q. I'll try and simplify things a tiny bit before we can move on to the double derivative. So nothing much really to do for the first term, but the second term these sine x's will cancel, so I'll get plus p cos x. And then the next term should be minus, but I put a plus now, so I'm going to do q cos x, and then go back a term minus qx sine x. Okay, let's differentiate again. I think I'm going to need a bit more room, so I'm going to move over here. So the first term to differentiate should be very similar to before. I'm going to write down the first bit that I want to think about, just leave it the same, and I'm going to differentiate the cos x, which is minus sine, as before. Then I'm going to write down the second bit, the cos x, and I'm going to differentiate the first bit. It's another chain rule. I'm going to write down the derivative of ln of x is 1 over x, so 1 over sine x in our case, and then times by the derivative of that, which is cos x. The next two terms are quite nice, minus p sine x and minus q sine x. And then the last one is going to be, well, I'm going to do a minus in a bracket. I guess I'll leave the q here. If I write down the x and then differentiate the sine x, and then write down the sine x and differentiate the x, which will just be 1. Okay, let's simplify things slightly. So minus p ln sin x sin x. Nothing really cancels out here, but I'll put the two cos x's together. So we get p cos squared x over sin x. Minus p sin x minus q sin x. And then if we expand this bracket, minus x q cos x. And then we'll have minus q sin x. But given that we've already got one from a previous term, I'm just going to make this minus 2q sin x. And that's our lovely expression for the second derivative. Now we have the joyous task of subbing that all back into the original differential equation and seeing if it equals cosec x, or seeing what values of p and q make it equal to cosec x. So I'm going to start with a brand new page, so I've got in as much room as possible. I'll just copy what I had down from before. So I'll take the second derivative and I'll just do it term for term. So nothing's changing here. And then I'm going to add on the original y, which is still in their question there. So I'm going to add on the p ln sin x plus qx cos x. And that should be equal to cosec x if we are to believe the question. Now you'll notice that these two terms cancel out. And these two terms also cancel out. So this is thumbs up for me, this feels good. So from there, if I write down what's left, we've got p cos squared x over sin x minus b sin x minus 2q sin x equals cos x, again, if we believe it to be true. Now, sin x is, cosec x is 1 over sin x, so what I'm going to do is I'm going to times sin x on the left and the right-hand side of the equation, and we're going to get p cos squared x minus p sin squared x minus 2q sin squared x. And if I times the right-hand side by sin x, I should be getting 1. This looks similar-ish to the original equation, the original question, but there's still a cos squared, so I'm going to get rid of that by using 1 minus sin squared. And what's left is expanding the brackets and putting it in the form in the question. So I've got p times 1, which is p. There's minus p sin squared and another minus p sin squared, which is minus 2p. So I can put that in a bracket like this, and there's a minus 2q, which I'll do as plus 2q, because then when you expand it, you get negative. And that's almost in the right form. Just one more thing to do is factorize out the 2. Like this. Technically, the question has the equivalent sign, the 3 equals, so what I'm going to sneakily do is add a third equal to all of my equations. Now it looks perfect. Now the hard bit is out of the way, we can find the values of p and q. This expression must be true for all values of x. So what I'm going to say is, well, if it's true for all values of x, then p minus 2 lots of p plus q times whatever sin x could be. So, for example, 0, if x is equal to 0, it still should be true. If x is equal to anything, it still should be true. Then we'll get p is equal to 1. That means that if I put in the value of p, like this, then it should be equal to 1. Now, for still all values of x, so we've got to find the q which works. Well, if I minus 1 from both sides, if this is always equal to 0, then that bracket 1 plus q has to be equal to 0, because sin x changes, it goes up, it goes down. That means q must equal minus 1. So we found p, and we found q. The last part of this question is just to justify the range of solutions which are valid, and also give the general solution. General solution is the complementary function plus the particular integral. So it's literally just a copy and paste from two previous parts we've done. So the first part was the a cos x plus b sine x, and then we're just going to add on the particular integral with the values of p and q included. So 1 times ln sine x, and then minus x cos x. The range of validity is going to be given, well, I'm going to be looking at the ln sine x. Sine x can go up and down between -1 and 1, but ln of something, that something inside has to be bigger than 0. For sine x to be bigger than 0, the values must be between 0 and pi. And here are two more tricky ones for you to try.